Hello viewers, in this class I would like to discuss on shear building concept. A shear building is defined as a structure in which no rotation of the horizontal members at each floor level is allowed. Since all the horizontal members in the structure are completely restrained against the rotation, the structure behaves like a cantilever beam which is completely deflected, that should only by the shear force. So the shearing force should dominate here in the structure to have the deflections in the horizontal elements. So here in this picture we have the two floor frame, the two columns on either side connected by two beams at each floor level. So for this we have got some assumptions to have the idealization of the shear building. So the total mass at each floor level is concentrated at a one lumped mass, that is again at the floor level itself, instead of the any distribution mass like that. Means whatever the load is there on the floor, that should be concentrated at the each floor level. And the second assumption, the horizontal members on the floors are infinitely rigid. These horizontal members on the floors are infinitely rigid as compared to these columns. As now just now we have seen that, or we have discussed that the horizontal elements are restrained against rotation, so the horizontal members on the floors must be a rigid one. So that means the flexibility of the beam and slab is ignored here, and the mass of the column is also ignored in this particular assumption. And the next assumption is deformation of the structure is not affected by an axial force in the column. Whatever the deformations are expected to have in the columns, that should not be affected by the axial force, particularly in the vertical elements, which is column. And the next assumption is the stiffness due to column and inertia due to slab are considered. The stiffness of the column is considered and inertia effect is also considered in this particular assumption. And the next one is no joint rotation in the structure. As now it is discussed that each joint of the horizontal elements are restrained against the rotation, that is nothing but the joint rotation is not allowed. And the next one, the load acts horizontally so that slabs move parallel to each other. Means the movement of the slabs in the parallel direction is seen. Means the loads are acting at the horizontal direction, the slabs on the different floors are moving parallel to each other. So in this particular screen I have taken one example of a frame. Considering a two-story frame, as now you can see in this picture, this frame can be idealized as an equivalent system. This is idealized as equivalent system, and this particular structure is lying or obeys all the assumptions of the shear building. This particular structure can be considered as a shear idealization or shear building. Shear building means which obeys all the assumptions which are discussed just now. So in this frame, I can take this frame for the consideration. In this frame, as the column stiffness is considered, right? The column stiffness is considered, that is K1 and K2, and the mass at floor levels are lumped, which is M1 and M2. Because of this, horizontal forces are seen in the elements, at the horizontal elements, and horizontal displacement is seen in the direction of this x1 and x2. So this column has L2 length and this column has L1 length. Maybe L1 and L2 are equal or may not be equal, and Young's modulus of the elements are similar, but moment of inertia of the section is different, may be different or may not be different. That is why I do take EI1 and EI2, right? So in this considerations, what we have done, the mass at floor levels are considered M1, M2, and stiffness at floor level are K1, K2, and the EI values are considered with respect to the cross section dimension. It may be EI1 or EI2 at each floor level, and the length of the column L1 and L2, because of the horizontal force seen in the elements, the displacements in the direction is seen, x2 representing displacement at floor level 2, x1 representing displacement at floor level 1. So now this particular structure, I would like to take an equivalent system. I would like to draw an equivalent system for this one. To draw the equivalent system, I do consider this one. I do consider this system, that is, this is connected like this, and means these are the two floors. This is M2 and this is M1, and this is K2, this is K1. The mass M2 and K2 and mass M1 and K1 means the stiffness is shown like this, like a spring, and displacement with respect to the my M2 and M1 are seen. This is for M2 it is x2 and for M1 it is x1. So which we can write that equivalent system. So for this equivalent system, I would like to consider the equation of motion. So for the shear building, I would like to write the equation of the motion for two-storied building. So however the equivalent systems is considered, so free vibration of the undamped systems is referred here. It is free vibration of undamped system. Free vibration of undamped system. So for this, I would like to take an free body diagram of this equivalent system. So as we have discussed in the previous session, that the equation of motion of a structure is drawn as a free body diagram for the three-story structure. Now here in this particular discussion for the shear building concept, I have taken two-story structure, and that structure is written in equivalent system, and that equivalent system is written as a free body diagram. With reference to the equivalent system, the assumption that the two masses are considered to move only in a horizontal direction, means only in this horizontal direction, and x1 and x2 are the displacement at the this mass 2 and mass 1. So if I draw the free body diagram of this, so first one I have the mass 1. Here there is a force which is acting on this direction, that is K2 x2 minus x1. This is the total force which is dragging or moving in this direction. To resist this force, another force is acting over here, which is m1 x1 double dot and k1 x1. Means the stiffness at this direction with respect to the displacement and acceleration in this direction is resisting this force on the other side. And at the same time, if I would like to write for free body diagram for the another equivalent system which is mass m2, so here in this direction I do not have any forces, because as it is in this part it is having no any forces or system connected, so no forces will act in this direction. In this direction the forces are expected to have, which is again nothing but K2 times x2 minus x1, and this is m2 x2 double dot, right. So in this direction this force is expected to have, in the other direction we do not have any force to act on the mass m2. So now once we got this free body diagram, the governing differential equation of motion can be obtained by referring to these free body diagrams of mass m1 and m2, which can be obtained by applying Newton's second law of motion, So the governing differential equation is to be obtained from the free body diagram of this one. This is the free body diagram of the equivalent system. So from this, if I would like to write the governing differential equations for m1, now for m1 I do write, if I do write, so what I can write, so in this direction the forces are written in the positive, in this direction it is negative, as like in the previous session what we have discussed. So m1 x1 double dot in this direction, and along with that plus k1 x1 is another force which is acting in the same direction. Opposite to that minus k2 times x2 minus x1. So since it is considered a free vibration, so which is equal to 0. If it is a force vibration, here it may come with f with respect to time t. And this is written for mass m1, and similarly I would like to write it for mass m2. So before getting the mass m2, yes, I will write that. So m2 x2 double dot, right, this is in this direction, which is plus, and plus k2 times x2 minus x1 and equal to 0. I do not have any other equations over here, means to write this for the mass m2. In a similar way, I would like to rearrange these terms. Just for the simplification. So to write to rearrange these terms, what I can do, so now here this equation I would like to write in the arrangements, right. So this is m1 x1 double dot plus I will multiply these terms. So this k1 x1, this minus k2 x2 if I multiply this here, and if I multiply this is minus k2 minus x1, that is plus k2 x1, right. So I will write this one, this is k1 x1 minus k2 x2 plus k2 x1, which is equal to 0. So this would be m1 x1 double dot plus, so in this k1 x1 and k2 x1, so x1 is common, what I can take k1 plus k2 times x1, and remaining is minus k2 x2. And in a similar way, if I write the second equation, governing differential equation, that would be m2 x2 double dot plus k2 x2 minus k2 x1, which is equal to 0. That what I have done, I have just multiplied k2 x2 plus into minus minus k2 x1, right. So this is the governing differential equation for the mass m1 and mass m2. So now I would like to write in matrix form, in the matrix form. So how I can write? By referring to the equation, by referring to the equation of mass m1 and for mass m2. So first I do refer this x1 is x1 double dot which is associated with m1, so this is m1, and in the same equation we cannot see m2 which is associated with x2, so it is 0. And now I am referring the equation number 2 to write this mass matrix. So in the mass matrix, x2 double dot is associated with m2, so x1 double dot is not there, so it is 0, and x2 double dot is m2, right. This is the mass matrix of the system, and which is multiplied with x1 double dot, x2 double dot. So if I multiply these two again, I must get the equation 1 and 2, and plus this is the acceleration matrix, this is the mass matrix. Now I would like to write the stiffness matrix. Since I have the stiffness over here, this k1 k2 values, right. So now I am considering this mass equation m1. In this, the x1 is associated with k1 plus k2, k1 plus k2, right. This x1 is associated with k1 plus k2, and x2 is associated with minus k2. In the same time, at the same time, for the second equation, x1 is associated with minus k2, x2 is associated with plus k2, right. This is the stiffness matrix. This is the stiffness matrix. Now the displacement, which is x1 and x2, right. This is x1 and x2, which is equal to 0. So what I have written, I have just rearranged the terms. I have just rearranged the terms and written the mass matrix. Here it is a mass matrix, and it is acceleration, and it is stiffness, matrix, and this is displacement. This is displacement. So now it can be, this particular equation can be written as m x double dot plus kx which is equal to 0, and this equation is called equation of motion for undamped 2 degree of freedom system subjected to free vibration. This equation is considered or called as equation of motion for an undamped 2 degree of freedom system. Degree of freedom system which is subjected to free vibration, right? Subjected to free vibration. So this is a shear building concept, right? So in this session, what we have seen, we have discussed on the shear building concept. We have taken a frame structure with the 2 floors, and displacement at each floor level is seen as x1 and x2, and mass at m1 and mass m2, and k1 stiffness and k2 stiffness for each column. And this is the equivalent system for the shear building concept, and for this equivalent system we have taken this diagram. So since it is the foundation at fixed end, right, and the column k1 and column k2, the mass m1 and mass m2 are representing connecting to k1 and k2, and the displacement with respect to m1 and m2 are written as k1 x1 and x2 here. And for this equivalent system we have written the free body diagram for m1 and for m2. We have written the free body diagram, and which is k1 x1, m1 x1 double dot is acting in this direction opposite to or resisting to the force acting in the horizontal direction on the forward motion, which is k2 times x2 minus x1, and which is connected to the mass m2, and mass m2 is having the acceleration m2 x2 double dot, and the stiffness resistance is k2 times x2 minus x1. So these are the 2 equations which we have rearranged the terms for mass m1, and we have come up with this m1 and m2. So by referring to these equation you can say 1 and equation you can say 2. From these 2 equations we have written the equation of motion, or the that equation of motion in matrix form, and this is the mass matrix connecting to x1 and x2 double dot, acceleration matrix, and the stiffness matrix are seen from equation 1 and 2 associated with x1 and x2, and which is equal to 0. This particular equation can be expected to have this like this, mx double dot plus kx which is equal to 0, which is nothing but the equation of motion for an undamped 2 degree of freedom system which is subjected to free vibrations. So particularly on this concept we will be having some numerics. The numerics will be discussed in the next session. Thank you.